We are very fortunate to have Dr. Matthew Lungren here for our talk today. Dr. Lungren received his bachelor's in English literature, so he's a kind of a Renaissance man here, and also a BS in biology from Arizona State University. He then went to medical school at the University of Michigan, and he received the university's Radiology Outstanding Scholar Award there. He then went and did his radiology residency at Duke University, where he was chief resident as well. He did a year of adult interventional radiology fellowship while also doing his master's in public health at the University of Chapel Hill. He then decided he wanted to do pediatric interventional radiology and studied that at Cincinnati Children's and was subsequently recruited to Stanford University. He is currently co-director of the Stanford Center for Artificial Intelligence in Medicine and Imaging. He's an associate professor at Stanford University Medical Center. He's a very productive academician. He's NIH and NSF funded, and he has done a lot of work in the field of artificial intelligence and deep learning in medical imaging, in precision medicine, and predictive health outcomes. And he's been very active in global health, using these technologies for global health. He's a very sought after speaker, speaking at national and international meetings on the topic of AI in healthcare. And we're delighted to have him today. He's going to talk about attribution theory and automating radiology with machine learning. Matt?
Oh, thank you so much for that kind introduction and the warm welcome inviting me here to speak with all of you. It's funny that when I talk about Arizona State, I always call it the Harvard of the Southwest. And my former chair, Sam Gambier, the late Sam Gambier, who recruited me to Stanford, was also an ASU grad. But a lot of people don't know that Sam actually graduated undergrad at Arizona State when he was 17. Whereas it took me about 4 or 5 more years than he did. But nonetheless, we're proud of it, and I'm really talking with you guys today. The title of my talk is going to be Attribution Theory and Achieving AI Automation in Radiology. And we're going to kind of go through some slightly non-traditional workflows here, I think, to sort of stimulate you and get you thinking about different ways we can use these technologies. These are my disclosures. So, I think we talk a lot about what's possible in a lot of these, kinds of discussions. Certainly there's a lot of hype that we've all been, a part of for a long time. But this is really a legitimate list of things that are challenges, right? Challenges for what we're trying to accomplish, particularly as we look to automate radiology. And, we've come a long way, but again, it'd be disingenuous for me to say that we still have work to do. And so this, so I spent half my time in the OR, the IR suite, doing procedures, and the other half is sort of a mix between the Amy Center and running my research lab. And of course, since March, everything's been at home. And instead of walking by and chatting with Dan Rubin or Kurt in the hallways, nowadays I pass my kids and my wife in the hallway and, chat between classes while they're at school and I'm at work. And, there was one time when I was on a call with some of my students and, we were struggling with some of the projects that I'll be talking about today. And my youngest son, who's in 3rd grade, he overheard me. And later when we saw each other, in the kitchen during our lunch breaks, which is kind of surreal, right? It's kind of like our water cooler at our house in between meetings. He showed me this superhero and from his class and, thought it might help me and said, whenever he feels like he's getting stuck, he just, thinks about his superpower of yet. And it was a funny moment for me because, we're all, I think, familiar. I'd heard of the growth mindset before. And, I was kind of blown away, right? Very insightful approach to challenges and things that we look to do on our own. And, I got it, I kind of got curious, right? So I looked into what's behind a lot of this. And at the root of that is something, called attribution theory, which is a sociologic field of study. And it's focused on understanding the explanations for individual behaviors and events, right? So we're the ultimate black boxes, right? We can't ultimately know what someone is truly thinking when they're doing something, saying something, or an event happens. And so there's a lot of learnings that we can take to the work that we do around causal inference and explainability. In particular, when we think about this growth mindset, that came out of work around learned helplessness and childhood psychology. Someone named Carol Dweck, who's now at Stanford, really pioneered this field because she kind of observed in her animal research that there's this, animals that are capable of doing things just kind of give up when they're faced with challenges. And she wondered whether this is also true in children. What causes, children to succeed or fail and keep trying? And, this is not just, a childhood individual sort of a phenomenon, right? This is actually a cultural thing. And, this can be contagious, this idea of a growth mindset or learned helplessness. And it sort of helps me sort of frame how organizations and cultures and lab groups and even individuals, of course, are successful. And I think about that environment here in the Valley and at Stanford all the time. We tend to live and breathe this worldview that, we don't really think about what's possible. We think about how we can get there in any way we can. And, there's a lot of other aspects in attribution theory that I think are going to be instructive. And I'm going to try to go through some of this as we talk today. I see parallels that tie our world of, Ben Glocker's work in causal inference and sort of how we explain what the models are doing. And then also looking at the field as a whole, how these cultural perceptions that we have about what is possible tends to be, anchored into traditional views of how we approach medicine, how we deliver care. And we've been using these tools by and large as a way to reinforce our existing ways of delivering imaging. And if we could pull ourselves out of this sort of anchored position, maybe we can lead to new transformations and actually get these tools to the places that they need to be. So I'm going to cover a lot today. And like any good English major, I'm going to kind of start out with some things that are familiar to you. And hopefully by the end of this talk, I'm going to have reframed your thinking a little bit, and we're going to look around. We're going to be in a completely different place than when we started. And that's kind of the idea, is just running through this paradigm, thinking about attribution theory and our own perceptions. All right, so starting out with just this list, is this a list of challenges or is this a to-do list, right? So we're going to look at this and say, we're going to tackle these one by one, and we're going to get through this. But let's just talk about the why for a second. This isn't going to be news to you. This is obviously not an incredibly precise figure, but nonetheless, we recognize in the next decade, there's going to be an incredible, almost unfathomable shortfall of healthcare and sort of relationship to the people that need it. We also recognize that our ability to, train one another in medicine is starting to become difficult, right? So when we were, beginning to build residencies and medical school education, medical knowledge doubled every 50 years. So, you could take a few CME classes and, keep up on the knowledge pretty well and retire at the top of your game. Now, medical knowledge is doubling every 3 months, right? It's crazy. And so we are increasingly subspecializing to hedge this, but that's not a sustainable path, right? And so we're in a place where our information is just becoming too much to continue to use effectively. We're going to need new tools to address it. And of course, there's money. I'd be sort of remiss not to at least mention the fact that we're now in an environment where there's a lot of money being invested in these solutions, and the variable clown car of different startups and different companies who are trying to move into this space, and in various ways, but most of them are just kind of trying to address healthcare as it's currently structured. When I think about, what's necessary for success in this space, you can kind of look at the field and say, folks at Harvard and folks at Stanford and other academic medical centers are in pretty good shape. We have all the tools that we need to innovate, to lead, and really to redesign this field and to show what's possible, probably more than any other group. And so that's sort of the thinking and, the environment that kind of led to the creation of the Amy Center. Now, we had two big decisions to make when we started the center. There was only a few of us. We were radiologists, right? Kurt Langlotz, myself, and a couple others. And the initial idea was that this would be the Amy Center, Artificial Intelligence in Medical Imaging. That was the original name. But we had to decide what we thought the future was going to be. Is it going to be just, we're going to do our thing in radiology and someone else is going to do their thing in dermatology, and that's just how we're going to live here? Or Are we going to just try to open up the doors and say, let's go across medicine? Do we think that these tools and technologies have potential in other fields? And that's really how we, one of the reasons we grew so fast. And we now have over 120 faculty across 9 departments and 3 schools here and many different external collaborators. The other decision we had to make was, what's our mission? And this mission statement is pretty bland and pretty generic probably, right? To many of you, you've seen this kind of stuff before. So what are we going to focus on? Are we going to focus on ourselves, or are we going to focus on the world, the external, everyone else trying to do the same work? And that's where we added in this last little piece, the everyone part. And that's really going to sort of inform how our thinking is around a lot of the programs that we developed. These are some of the pillars, again, that we sort of turn back towards when we look to build out new programs and sort of organize ourselves. We look at collaborations, we look at education, we look at the actual data itself and the infrastructure, and then also how we can catalyze funding. And these are all sort of the core pieces of the work that we do. Now, I was just talking about this with some of your colleagues, these kinds of, assumed, resources that we all have, well, of course we can just get data and do this. Not so easy, right? When you start doing it and you understand that data science and data access are critical components to the work that we do, but often not given a ton of thought at the beginning, let alone these additional pieces that we're recognizing are going to be critical for the future state. And, just in full disclosure from our perspective, we are excellent in data science, if we don't mind saying. We have some challenges around data access even today, even after having worked on this for many years. Now that we're moving into cross-modality work, which I'll talk about, it's getting slightly more challenging, right? How are we linking these large data sets from different modalities together? And then finally, delivery. We're all struggling with delivery, partially because of the antiquated medical system, partially because of just culture, and partially because the technologies maybe aren't ready for us yet. Along the lines of education, many of you have possibly heard of some of the things that we try to do that are, sort of very much public and open facing to the general public. I mean, we certainly have YouTube seminars, we have research in progress, we have journal clubs where we invite authors of papers that we like to read and sort of get a chance to hear from the authors themselves. We've also done some things for our groups, like Office of basically a clinician experts in various, whatever domain expert is relevant. And then we have computer scientists and faculty that have open office hours. So they, you have a project idea, you're not really sure if it's going to work. You can schedule an office hour with one of our faculty and just spend some time talking about your project and working through it before you get too far. That's been really successful. We've done some happy hours, just kind of general discussions to raise awareness of different things that we're doing. And then certainly we've done large symposiums as well, really just trying to engage our audience. Another thing that we've done is sort of, we worked really hard to try to design a curriculum internally because we have so much interest from clinicians saying, I don't know how to get started. I don't want to learn how to code. I hate math, whatever it is, but I have a good idea. How do I learn what's possible, what's not? And so, we try to develop this curriculum, and it took us a long time to sort of build this out. And eventually we just said, we think it's at a place where maybe we could release it on a larger platform. And so that's what we've done. As of last summer, we now have a Coursera. You can get a certificate that's of interest to you, but you can audit it for free if you like. But it really tries to go through all the concepts and principles of the work that we're doing in deep learning and healthcare without having to, without the learner having to code anything. And really, it's kind of similar to the analogy of MRI, where I don't know how to build an MRI machine, but I can certainly tell you what's going to work, what's going to fail, where it might be useful, where it won't be. And that's kind of how we looked at this problem. Another thing that we've done, which maybe you're also familiar with, is we've really tried to make AI-ready data sets available to anyone who wants to work on this problem. We recognize people over the world are learning to code, they're learning deep learning. There's a million great resources out there by colleagues of ours, Andrew Ng being one of them. And then how do they sink their teeth into medicine? They want to work in healthcare, but there aren't a lot of data sets. Or if there's data sets, they often don't have labels. Or if there's labels, maybe they're not very good. And so how do we create an ecosystem of AI-ready data sets that anyone in the world can use, can benchmark, and can potentially innovate on? And that's really something that we believe very strongly in. It wasn't easy to do, and that's probably a story for another day, but in general, we've been able to contribute both to our sort of ecosystem of labeled data sets, but also to larger efforts like by the RSNA and the other challenges. Collaborations, right? This is important to us. This is a slightly older slide. I didn't have time to update it, but we now have 15 industry affiliates, several industry contracts. I mean, these are important to sort of fund the work that we do. We actually use it to help our researchers get seed grants and do innovative things with partners. And frankly, our students like it, right? They get to hear and see companies that maybe aren't the typical, Google, Facebook, Amazon, where they all tend to go when they graduate our labs. They get to hear about other industries that are doing exciting work. I wanted to touch on two partnerships that I think sort of illustrate how we've really tried to open the doors to diverse partners. And one of them is a company called IDEX. I hadn't heard of it. Maybe some of you have. This is a publicly traded company that deals with telehealth for pet care. As you can imagine, there's a shortage of radiologists in the world, but there's even more of a shortage of veterinary radiologists in the world. And they do a tremendous amount of imaging for their patients. But unlike sort of patient data, there's no HIPAA regulation. And so there's really this odd ecosystem of a lot of medical data, a big, huge need for telehealth services at the point of care for their veterinary clinics, and a lack of experts to do that. And so deep learning can play a huge role here. And so we partner with them, talked about pathology. They do telepathology, they do telelabs, they do teleradiology as well. And so there's a lot of really cool projects that I'd love to tell you more about in the veterinary space. And then we draw learnings from that environment back into the things that we do with human healthcare. So really exciting. Another cool partnership I wanted to tell you about is Fenwick and West. Now you're like, why is a law firm partnering with a clinical AI lab? And so what happens, at least in our environment, we have dozens of faculty, students who either want to do a startup, they're working as a consultant for a startup, they are reviewing a contract, they're talking about IP, they're trying to decide what's protectable. These are difficult questions. And Fenwick and West is one of the premier Silicon Valley law firms. In fact, they're very well known here, but certainly they made the news in the fact that they were one of the first law firms to raise the alarms for Theranos. So they're very good at what they do. And so we have office hours now for legal consultations. So they contribute pro bono hours to our center and as an in-kind contribution. And then people that are affiliated with us can take advantage of this and sort of get a lot of legal help for the types of things that they want to do in this space. So anyway, just some ideas around diverse partnerships that we've started to do. I won't belabor this. This is just sort of an idea. We had a seed fund for our faculty affiliated with the center, and we try to fund these kind of blue sky projects every year, and we've been building this out quite extensively in the last 2 years. All right, so let's get into some more familiar territory in terms of the nuts and bolts. Let's talk about imaging and deep learning. So this is a pulmonary embolism scan for those of you who aren't radiologists on the call. This is a CT of the chest. So, patients given contrast, they're scanned, and they're looking in this particular case primarily for clots that can form and travel to the pulmonary arteries. And in this case, this person has extensive bilateral pulmonary emboli. And so this is an important problem, right? Especially as we're seeing the relationship of this disease to COVID. But it's also an important problem for a couple other reasons. One is I really like it for deep learning, in particular because I don't have to have arguments about ground truth with anybody. I don't have to talk about what does the pathology say. This is kind of the gold standard test. There really isn't a lot of additional steps necessary to get the ground truth for this particular diagnosis. But in particular from the medical society as a whole, or for the medical community, this is a problem that is increasingly being noticed by payers and government bodies to say that there's a lot of unnecessary imaging. We're not making good clinical decisions on when to order these scans, and we're kind of doing a bad job and wasting a lot of money with treatment cascades and other things. So how can we design a system that does this better? And this isn't just my idea, of course. This is direct off the PAMA sort of priority list, right? Suspected pulmonary embolism is one of the key areas where we need to figure out how to get control of the costs and make better decisions. Now, the initial thought from, we have a hammer, this is a nail, let's go for it, right? Is really just to say, let's throw a deep learning model at the problem, see if we can automate the diagnosis. At least that could be a first step. And all the existing approaches in the literature that we had seen before we started this work were really computationally expensive. They had a lot of pre-processing, they did a lot of feature engineering, And they're just basically over-engineered, and they weren't capable of really being deployed in a clinical system. There's no end-to-end solution that was really viable before we sort of started to think about this. And what we needed was a computationally inexpensive way that could digest the whole series and kind of focus on what we wanted to do. So without belaboring that too much, we ended up going towards 3D neural nets, and we as you may know, you can pre-train on Kinetic 600 as opposed to ImageNet here, and then we used the squeeze excitation network architecture, which again, this was what happened to do the best at the ImageNet challenge. I think improvement was like somewhere around 25%. So this is work by Mars Wang, who's in my lab, a PhD student, and we were able to do fairly well here. So we were pretty proud of ourselves. Our model did well in our test set. We had an external validation set to make sure it could generalize to Intermountain Healthcare, and it did. We keyed up a little bit of a visualizer, and we felt pretty good about ourselves, right? So and this is of course pre RSNA challenge. You're welcome to read more about this work and then the RSNA challenge data set that came from this. But the reason I'm bringing this up is, I want to talk about something that we learned in attribution theory at the beginning, which is sort of the idea of perceptual salience, right? So attribution information often ignores external factors. So you kind of focus on the model. Why is it not performing well? What's actually happening on that imaging study? And you're kind of ignoring what we all know in the clinical world that's important, which is context. And we recognize that it's about more than just the pixel data, right? We know from our own literature in radiology that lack of access to the contextual data, the clinical data, is critically important, right? And if you don't have that, then potentially you're not going to reach the potential for your systems to do automated diagnosis. So what are some of those non-pixel elements that we can think about? Well, certainly it's the EHR data, right? That's a huge component of that. And these are just some of the things that in this use case are known to be risk factors for positive pulmonary embolism or DVT or pulmonary embolism. So these are risk factors that we can sort of incorporate into a workflow that could maybe give us a better pretest probability, right, before we order the study. So we worked on this with a group in Dan Rubin's lab and Chris Manning's lab, and so we tried to come up with a way to do a timelines of patients' data that occur before the CT scan is performed. We can do some feature engineering here to really feed these in, and this is kind of a high dimensional features but small sample kind of a problem. But nonetheless, we can come up with a prediction that will give us a probability as to whether the test that's going to be ordered is going to be positive or not. And this has a few potential advantages, right? One is if it's really low risk, maybe you don't need to order that imaging examination. Or if it's super high risk, maybe now you'll say, I'll give that person heparin now and sort of avoid some of the known problems with morbidity and mortality for delay in treatment for this kind of a problem. And this is work that was led by Iman Banerjee. She was now a faculty at Emory. So again, we looked at our model. Again, this is just based on EHR data. We compared it to the existing scoring systems that are in practice. As you'd expect, they didn't do that well. But of course, these are intermediate risk people. So these scoring systems aren't going to perform very well, but it's still a problem for us. And then we found that our neural net did generalize to Duke, where we didn't have any training data at that time, but we used them as an external test for our EHR model, and it did pretty well. And we published that in one of the JAMA journals. So how would this work from an EHR perspective, a workflow perspective? Well, you come in, you still get ruled out with traditional scoring systems if you can. But if you follow that very common moderate high risk where you're going to get the imaging examinations, you can potentially run this and move more people towards the low risk, no imaging route and try to reduce imaging. And we were able to find a decision point that was pretty reliable that allowed us to reduce the number of studies by around 18 to 20% without increasing false negatives, which of course would be highly problematic. And so this is another opportunity to use some of these tools to help our workflows. But you probably saw where I was getting ahead with this. Well, now we have this really great EHR model and we have this really great vision model. Can we put them together somehow? Is there an opportunity here to do some fusion, multimodal data fusion, and actually achieve something even more useful? So this is, we started to look in the literature, certainly the computer vision literature and other places, to see what kind of fusion modeling has been done. And, in general, we found that most people that use different modalities found an increase in accuracy for their studies. But, there's a lot of variance, right? And there's no one single approach that consistently led to optimal performance for these kinds of tasks. So we did a systematic review and then try to publish some guidelines and some ontologies around how can we start talking about this as a field, multimodal data fusion, and then what does that look like? And so again, you're welcome to check this out. But for the most part, we tried to break things down into different approaches to leveraging the data. So, in early fusion, maybe you're concatenating all the original features from the input level into a single feature vector before feeding into one model. Whereas joint fusion, there's a few different opportunities to do that with one modality potentially more than the next in terms of informing the loss function. And finally, you have this late fusion sort of schema, which is familiar to those of you in data science as more of an ensembling approach. So we did this with our PE use case, right? We had this vision model, we had this EHR model, and we in our work, we actually went through every different possible way we could figure out how to fuse them together, ultimately deciding in this particular case that the later fusion worked the best. But again, we did see that we did have that performance bump, as you might expect, right? You're getting contextual information that was not available on the pixel data. And here's just a couple of examples of from our paper, just demonstrating where the vision only model got it wrong, but the fusion model was able to pick those up. And that's recently published just in Nature Scientific Reports just a couple weeks ago, actually. Took us forever to get these out, by the way, how things go. All right, so I want to give a shout out to some of the work that you guys are doing. I'm really impressed by some of the learnings that we're getting from image to image comparisons with Siamese neural networks. This is work from Jay Cherie and Matthew Lee, who we've had a chance to meet. He's fantastic. Shout out to their work and this paper in particular, where we recognize that again, sort of in the attribution theory paradigm, there's this perception of causality, right? So we attribute the failings of humans doing these reading studies as, well, they didn't have prior examinations. So that's why they weren't able to perform as well as the model. Well, let's find a way to give the model the opportunity to compare across priors. That's a huge part of the job that we do as radiologists, right? You all know that. We need to know contextual information, as I mentioned before, but we also need to see from the pixel level what's changed, right, over time. And so this is an opportunity to do that. And so we've actually said, let's take a slightly different approach and see if we can do, the traditional Siamese, is sort of a comparing feature representations for similarity. But we try to take a different approach. So we took PET CTs, which are, as you may know, are very large exams, but some of the fundamental purpose of PET CT is to sort of know, is the patient better, worse, or the same? And I know that's very much I've reduced that to the minimum you need to know about PET CT, but nonetheless, there's something called the Lugano score, which essentially tries to quantify that as a change of 25% in sort of the study over time. And we try to take a supervised approach using the sort of the Lugano score as a label. Again, we used a 3D encoder here, and then had region-specific encoders for each of the body areas, so head, chest, abdomen, pelvis. And we took pairs, so we had 5,000 PET CTs, we had pairs paired up, so it'd be 2,500. And we got area under the curve for that decision about whether the study has changed better, worse, the same by the Lugano score. We're in the 0.84, 0.85 range already with this sort of approach, which we're pretty excited about, I think. And again, this is a shout out to Anirudh Joshi, who's my student on this project. And here's just a couple examples, which I recognize some of the challenges of trying to do explainability, but as opposed to CAM, this is actually this is a guided backprop instead of the traditional CAMs, where we can sort of do saliency to figure out which pixels in the original image, when changed, influence the outcome. And here, obviously, as you'd expect, it sees this new lesion, as you may recognize here in the rib, and that's obviously the reason for the change here. But this one, where you have two very hot areas, two obvious abnormalities, the saliency map in this particular case is blank, right? There's no significant signal in its decision to say that there was no change. So we're starting to say maybe it is learning some of the things that we hope it would learn, and this maybe give us some opportunities to compare across priors in more of a supervised or semi-supervised approach. So we're pretty excited about this work. As an aside, we did talk about, running it like a UMAP, and then try to have information about vectors on time points, but we haven't gotten there yet. All right, one last area I want to cover quickly is another concept of multidimensional feature space. So if we talk about, again, the perception of causality, where, can performance really be limited by your own attributes? And in this case, we're trying to say, can we do some things that are superhuman with our imaging examinations that can provide learnings from some of our models that humans really just wouldn't have insight into? I liken this kind of idea to the Twilight Zone. For those of you in the slightly my age category, or for the millennials out there, this is the upside down for the fans of Stranger Things. But really what we're trying to do is, can we take representations of embeddings of different time points on patients, and try to figure out a multidimensional feature space by which we can learn what happened to those patients. Are there clusters of health? Are there clusters of not health, right? I mean, it's okay. And then can we figure out their trajectory over time? And can we look at this as at a meta level in our healthcare systems? And if you can imagine now combining multimodal data with sort of this multi-dimensional feature space, could you maybe make better decisions as a healthcare system with maybe an approach that you wouldn't normally have? And for those of you who are trying to figure out what the heck does this all mean, a simple example is if you try to make a decision in this example between the orange circle and the blue square, you're not going to be able to do that, right? You don't have a decision plane for that. And as many of you know, in data science, this is kind of the kernel trick behind SVMs. You could add an additional dimension, right, without changing fundamentally the mathematical relationship between the different points, and you can find a decision plane, right? So we know this, right? This is all very common knowledge, and so this is kind of how we conceptualize where we can figure out how to group these folks based on different attributes that we can't necessarily see. My best analogy for this kind of a thinking is really, rooted in my nerdy interest in physics. I don't understand string theory. I'm not going to pretend to, but some of the additional dimensions, I think now we're up to 14. Maybe some of you out there know, maybe it's more. Kind of started with the idea of how are we going to relate, relativity to, traditional this quantum mechanics idea. So, again, there's a lot of cool books out there. I'm just going to put a plug in for this one. It's a lot of fun to read. But if you're really trying to think about how we can use learnings from other fields, other approaches, and bring it back into our own domain, this is one way to do that. And so again, we have projects that are now working towards figuring out where these embeddings could lie for our patient populations, and then trying to make decisions about, can we predict trajectories of our different patients in our healthcare system. And this is work led by one of our brilliant postdocs, Joseph Cohen. All right, that's a lot to go through. I told you there'd be a lot, but I also wanted to take a step back and talk about the cultures that are anchoring us to our thinking. There's the radiology-centric approach, which is pervasive, right? Where most of us working in this field are either radiologists or are working with domain experts in radiology. And this is going to cause a framework of how we're going to approach these problems that may exclude other possibilities that we're not going to consider because we're really not in that line of thinking. Again, this is part of the idea of dispositional inference. Okay, so who are these other folks? Well, it turns out that there's a lot of people out there that aren't radiologists that use imaging. There are, just as an example, there's 250,000 plus primary care clinicians in this country, and there's about 40,000, give or take, radiologists. So a large amount of people out there that use imaging in their day-to-day practice that are not radiologists. How can we help them? Is there a role for that? I would argue that there is. They would argue that there is. In the current workflow, and again, in our country, which is well-resourced, you come in, you see your doc, maybe they order a chest x-ray, but now they're going to wait. They're going to wait to hear what the radiology report says. Now, turnaround times, maybe you guys are great. Maybe you're getting your turnaround times, down to minutes, but most systems don't have that. And particularly if you're in a more rural setting or in large healthcare systems that are spread across the country. And this is because radiologists are super busy. We've maximized efficiency. We've moved to a commoditization. And again, a lot of solutions that we've talked about are focusing, how can we make the limited resource of the radiologist better, faster, more efficient? But if we take a step back and look at, can we now maybe create an environment with some of these tools that would make the primary care doc more efficient and capable of doing some of these things? And that's really a difficult, this is a challenging concept to many of you, and I understand that. But it's also something that we need to consider for some reasons I'll get into in a minute. But let me give you a concrete example of where this could really help us. So this is pre-COVID. Clearly, this is actually when I was used to be able to get haircuts, actually. And this is Nat Dean. This is the chair of pulmonary critical care at Intermountain Healthcare. We have a large partnership between Stanford and the Intermountain Healthcare system. And he's the creator of a tool, a clinical decision support tool known as ePneumonia. And he reached out to me after some of our really early work in pneumonia and x-rays and asked if we could collaborate. I said, sure, why not? This will be fun. This is actually, I'm circling here, the very sophisticated data transfer that occurred for this project. The lawyers at Intermountain refused to allow any remote access to data. They had to bring it on a hard drive on a plane and deliver it in person. It's a long story. But anyway, we don't have to do that anymore, but that was how it started. All right, so what is ePneumonia? How does it work? Okay, so what he had designed was a system where he wanted to help his clinicians in his practice, use the best care pathways for pneumonia, treatment and diagnosis and disposition. So he needed the chest X-ray. That's a critical piece of information. So he used Cerner's, which is their EMR. He's their baseline NLP to extract structured data elements from their free text reports and combine it with EHR data that was relevant to the diagnosis, and was able to create a tool that kind of was really great. It actually worked in the EMR, and in a very small study initially, he was able to show a 30% reduction in 30-day mortality, really great adherence to best practices, which made everybody happy in the healthcare system. But the reason he came to me was that the MD utilization rate was 20%, and that's probably an overestimation. No one was using it. And so he's like, he just couldn't understand why no one would be using this tool because it was so effective. Well, let me give you some ideas of why maybe it wasn't being used. So here's how the workflow worked, right, in their system. So you got the chest X-ray, the radiologist needed to interpret it, then the report had to be dictated and signed, then the Cerner NLP had to run and extract the labels, and then it could run the tool, okay? This time, so again, in maybe in Salt Lake Valley, it's 20 minutes, but out in Nevada and some of their external clinics, 6 hours, 10 hours, sometimes 24 hours, urgent care docs were waiting before they would get a final read on some studies. This is not going to work, right? This workflow won't work in this current era of Press Ganey scores and patient satisfaction and really making the best decisions. So the idea here then is, can we insert a pixel-based tool that can extract those same structured data elements without having to wait for a radiologist interpretation, and then run the tool in the same kind of workflow. And it, again, takes less than a second to do that. Advantages here, of course, you don't have to wait. We talked about that. The other advantage, of course, is maybe those of you who are savvy to NLP recognize that there's a lot of potential for error there, right? Free text reporting is already difficult for those of you who do that work, and imagining trying to do it from a kind of a rudimentary model like the one that Cerner uses at baseline. And then finally, physician variability, which I think is grossly miscalculated in a lot of work that we do. Maybe you haven't had a cup of coffee, maybe it's late in the day, maybe you had a long shift, maybe you're on the phone looking at another study. And there's a lot of variability they found in their own system, so we could be more consistent with a tool like this. So we did some initial work retrospectively to kind of really dig into this, comparing the NLP, comparing their expert physician consensus labels on a very large test set, and then also our new model to see how it would perform. And we found that on average, it was better certainly than their existing system, but then kept pace, and in some cases was a little bit better than their physicians on average. This is work led by Jeremy Irvin, by the way, postdoc. So we said, let's just do a trial. Let's do a clinical trial for implementing this potential solution. It's pretty straightforward. This isn't going to require a lot of charts and graphs here to tell you that you're referred for a chest X-ray. We're going to randomize to the standard of care ePneumonia, or we're going to randomize to ePneumonia, AI we're calling it, or CHECS-ED. We have a few names. We can't seem to decide. But we are able to get this funded finally as an R18 through the HRQ. And so, it's ongoing now. We have some primary outcomes which we will easily meet just based on how we designed the study. But then we have a lot of secondary outcomes that I think are going to be really informative. Really excited about this trial, particularly as we're in the COVID era, and we're already starting to see some very exciting results. I'll be able to share those with you hopefully by the end of summer, early fall this year. And again, this is again a way to say multimodal data fusion, point of care, new workflows. Can we really reinvent parts of our system to make healthcare better? And speaking of COVID, I like this slide because we always talked about different things that we'd want to do, and then the COVID era hit, and then now, of course, the biggest change agent is really this pandemic, right? There's a lot of things that have come from this. Certainly in our own healthcare system, I'm sure you've seen the same kind of thing. I want to point out one thing that's very that caught my eye. That I don't know if you guys have seen this, but the idea that now our EMR vendors are increasingly building in what they're calling cognitive layers and ability to do some of the deep learning. As you saw, Epic has partnered with large cloud vendors, and so has Cerner. Are we going to be at a place where now the primary cares and other specialist physicians who are not radiologists are going to be driving the innovation here? And so here's an example of a tool that was tested at University of Minnesota, again, on the imaging data, but the results were given directly to the clinician, and that did not pass through the usual workflow of the radiologist, at least for the initial results. And that comes through the EMR, guys. That's not coming through the PACS first. That's not coming through some platform of which there are many out there. This is coming through the EHR itself. And so recognizing that this pandemic, certainly the push and all the other factors I talked about, are going to start to change what it means to be using imaging in our healthcare system, particularly as we have these deep learning tools. And not to belabor the point, but there are a few people that you may have heard of entering this space in a big way. Walmart Health, they like to say that 95% of the US population, 95%, live within a 15-minute drive of a Walmart. Doesn't matter if you're in the middle of nowhere, you can usually get to a Walmart in about 15 minutes. So they are recognizing a huge push in healthcare is a strategic advantage, and they're investing heavily into resources to do most of the care in a Walmart. And a lot of market reasons for that advantage. And obviously Amazon, huge push into this space as well. You may have heard about how Maven didn't exactly, blow anybody away with what they've accomplished, but it was really partially because Amazon has so much work going on into their, Uber for healthcare kind of environment where they're empowering things at the edge. They're really trying to reinvent sort of how care is delivered, and deep learning is going to be a big part of that, and certainly around imaging. So this is why some of these forces may not be so mysterious in the next few years. All right, so going back to the cultures, we can anchor ourselves again, as we've just done, in sort of this point of care, patient-facing clinician workflow where you do have imaging services, but you have plenty of infrastructure and resources. And let's take a step back and look at the population level or the global health level, which is something that I'm particularly interested in. So again, this comes as a surprise to an American audience that 95% of the world does not live in North America. Again, I say this somewhat tongue in cheek, but we tend to think of the world as very much revolving around us being North Americans, but that's simply not the reality of the world. And yet, of course, we do see most of the innovation and spending and I guess attention being paid to us, mainly because we spend a lot of money on healthcare, right? And it's obviously a huge market. But when we look at some of the reasons why AI is going to, really need to move into radiology and what it's going to do, we turn back. Of course, I love Kurt. He's my boss, right? I don't want to say anything bad, but clearly he is positioning our field to say radiologists who use AI will do better than radiologists who don't, and I wholeheartedly agree with that. But when you ask the question, where are the radiologists that we're going to help? Well, they're in Western Europe and North America. And the radiologists per million population begins to be vanishingly small in, again, most of the world, which again covers most of the population of the world. So how are we going to find a way to deliver these solutions and to really get to a place where we're actually impacting healthcare if all we're focusing on is our existing, our North America, Western Europe kind of usual suspects? How are we going to do this at a big scale? So I kind of amend this tweet. I do this tongue in cheek, but I do think that now we have an opportunity to leverage clinicians, point of care clinicians, to leverage some of these tools to make decisions. And again, this is on a global scale and not just in the, Walmart clinics and Intermountain Healthcare. I'm talking about how can we bring this to the global population. So we kind of dipped our toes in the water on this idea. So we had done a lot of work on providing models to orthopedic surgeons, providing it to pulmonologists, as you saw, for very narrow use cases. We also had an opportunity to partner with a group in the University of Cape Town in South Africa. And there was a group of pulmonologists there that ran a TB clinic for HIV patients. And so this is a very subspecialized kind of part of the world and a very, region-specific disease problem. But nonetheless, this is a resource problem as well, right? They don't have enough radiologists certainly to do this work with them. And they were forced in this particular case to do all of the imaging interpretation pretty much on their own with rare exceptions. We developed a tool for them. Again, this is not like, startup level quality. We don't have millions of dollars in seed funding, but we were able to put something together that we called ChecksAid, which just said, can we leverage a multimodal data model that could look at the pixel data, some of the clinical information, and help their clinicians make decisions on whether this patient is likely to have TB or something else. And again, the something else is there's a variety of diseases that can occur in this patient population. This is work, I should mention, led by Pranav Rajprakash. So, we found that, on average, their baseline performance with the ground truth was modest, right? Not too great, but, they're trying the best they can. This is where the expert South African radiologist we convinced to help us with this project fell in terms of performance. This is a hard problem, right? This is not a simple solution, but they certainly perform better. I took the test just saying, how hard could this be? I won't be recruited to South Africa to be a radiologist. I can tell you that for sure, because this problem turned out to be a lot harder than I gave it credit for too. But we eventually found that when we could provide them the assistance of the model, and now again, this gets into some other things I won't have time to cover, like automation bias and the learnings about probability and what we found when we changed, the way we displayed the output of the model. But nonetheless, we were able to increase the performance by a modest amount and feel as though we have some signal here to pursue some ideas in this space. So this brings me to this problem, right? So now we're talking about, well, Matt, you're talking about this global scale thing. I mean, we can't even get, maybe in your case, you can't even get Brigham and MGH to use the same workflows for your Epic templates, right? How are we going to do this for a global population where you have, folks using digital, you have folks using film? How is this possibly how can we deliver any of these tools on a population scale like you're talking about? And, some of you may have heard me talk about this before, but we're going to use the smartphone. We're going to go straight to the edge. More people on the planet have access to smartphones than they do to clean water. This is just a fundamental technology that's transformed our society at large. The unique number of mobile phone subscribers will be at 6 billion by 2025, which is about 70+% of the world's population. And most of this growth is really led by developing countries. And again, there's this incredible heterogeneity that we could potentially deal with in the healthcare environment if we're working on point of care via the edge. So you might say, Matt, this is ridiculous. No one's going to use smartphones for medical diagnoses and clinical practice. And I'd say maybe you're wrong. This is a study from the NHS. This is clearly a good healthcare system where 50% of their physicians admitted to using picture messaging to consult a colleague. Maybe it's a picture of an X-ray, say, hey, can you look at this really quick? Maybe it's a skin lesion, whatever. But this is not completely foreign to healthcare, right? The idea that you're going to use your smartphone to help make decisions. And then you might say, well, the quality can't be that good, right? So how could they possibly make diagnoses that are on par with, a radiologist at a workstation? Well, again, there are plenty of studies. This one in particular is showing that when they compared WhatsApp text messages of pictures of imaging examinations, in this case, chest x-rays, to someone sitting at the workstation, there really wasn't a significant difference in the ability to make important diagnoses. So there is enough information on some of these sort of workflows to really do the right thing and to really help inform care and make things work. So, okay, so how are we going to do this? So really what you're talking about then, Matt, is you're saying you're going to take a smartphone, you're going to take a picture of something. Well, that's going to introduce artifacts. The model wasn't trained on smartphone photos. The model was trained on, the original image. You're going to have all kinds of problems. And so we needed to create a data set, part of which was created synthetically, to perturb the data in a way that would allow it to be robust to all of these artifacts that are going to come up. Matte glare being the main one for film, and moire artifact for taking pictures of screens. And so we actually worked for a long time on this. This was a huge blocker for us. This was the power of yet moment for us. And Sharon Zhao led a lot of this work, and we were able to overcome a lot of problems with our models not performing as well when we use pictures as opposed to the native image. Some of this did involve some unfortunate manual labor that will go down in history as some of the most painful lab work ever, taking pictures with some different smartphone cameras from different angles and different lighting conditions to create a data set. And really, these are some of the main artifacts that we were kind of coming up with. So again, not to belabor this because we're wrapping up towards the end here, but we've done a lot of work in this space. We've actually released our entire data set of that we call Checks Photo. If you're interested in training models on photographs of film or screens, there's actually more papers than I'm showing here. Again, this is brilliant work led by Pranav Rajprakash, where we're really trying to push this as far as we can to the edge. So we have a smartphone app now. Great. So does everybody, right? Everybody can do this. Taking a picture of something, running an analysis, and coming up with some information. What do we need to do to get this into a clinical trial at a global scale? Besides, hundreds of millions of dollars, we would need a trial platform. We need this thing to already be available in thousands of institutions worldwide. We would need to have something that's approved for national and international privacy laws and regulations. We would need local PI stakeholders that are familiar with this platform. And then finally, some kind of secure smartphone option. So, and oh, by the way, it has to be free and open source because I can't pay for anything. I'm an academic, right? So this is what we would need to move forward. Seems almost impossible, right? Well, let me introduce you to something called REDCap. You may have heard of REDCap because it's used very regularly for clinical trials all over the world. And the beauty of this system is that, number one, it's incredibly ubiquitous. Number two, it's free. And number three, it's really already approved for every possible international local hospital regulatory body. In other words, for these 1 million plus projects or users, they're able to, perform protocols for clinical trials and enter that data and perform their portion of the trials in 131 countries, right? So this is work initially started by Vanderbilt University in 2004. And again, this is currently in 4,000 institutions or so. And they have a smartphone app. So this really seems to be a very fertile ground for potentially what we're looking to do, which is to trial some of these point of care models running inference on the edge and helping with clinical decision support. But the problem now is that we need to get the model that's sitting in Python, and we got to get it to a format that it can be used. And so we had to use TensorFlow.js. This is Arjun Sun's work, really working to convert our models and come up with a very clear pathway on how to convert them into to be used in the REDCap environment. So we'll have a paper coming up very soon that details a use case in chest X-ray and dermatology for how to basically bend REDCap to your will and use it for this use case, which it wasn't intended to be used for, to collect data, to provide information, and then to run a trial. And so we think that this is going to be a viable way forward for hundreds of partnerships that we're forming through the REDCap network. And we'll be speaking at the REDCap conference. I'm guessing it'll be virtual, but to talk about what the other PIs can do with their models if they want to use this kind of a workflow. Okay, so that's a whirlwind tour. We kind of started right in some familiar waters, and we've kind of moved into a place where maybe you didn't expect us to be, and that's kind of the idea here. We really want to get out of our traditional ways of thinking, and we want to think about this as a to-do list and not as a list of insurmountable challenges. And so that's what we're working on now. I would definitely want to remind you that, again, we are trying to do this for everyone. We're doing the best we can, and certainly we will have challenges and setbacks along the way, but ultimately we think we're doing the right thing. So thank you for listening. Thanks for the opportunity to speak with all of you. And, I'm hopefully able to take any questions you guys have about what I've talked about. Thanks.
Matt, fantastic presentation. Thank you so very much. And folks who have questions, please go ahead and type them into the chat box or the Q&A. I think it was a wonderful talk where you you really went across a number of things. I loved your description of how you started your center and how it is multidisciplinary, and went into some of the mechanics of how you got started with some of the things that we're dealing with as well in terms of the data acquisition and so forth. We do have a question, let me see here in the chat box, in the Q&A. So let's see the question here from Rayview. How do you attract and keep AI talent while you're sitting in the heart of Silicon Valley?
Well, the short answer is we don't. I mean, we just accept the reality that, we're going to have these incredibly brilliant, talented people for a short time. At least in my lab, I make it very clear that my job is to get them a great publication, but also get them into a job that they want to have. And I try to expose them as much as I can to the fun of, the academic environment where we do have this, blue sky, greenfield kind of, world that we can explore whatever we want. And, try to shield them from some of the drawbacks of being in this space. But ultimately, again, most of my students, and frankly, people that come from the Amy Center, they go into startups, they go to Google Health, but, occasionally they are doing internships with, some less known companies. And I think part of that's because of their exposure via the Amy Center. But, in general, we hope that we can find talented people willing to dedicate a couple years of their lives and their education with us, and then pass it on to the next group that comes through. And again, sometimes it's sad, right? There's moments where you're just like, man, we just had such a great team, great chemistry, and you're sad to see it, kind of dissolve. But if you keep the culture fun and interesting, and everyone has a say, and we have a lot of creativity, I think, again, you continue to build that same feeling with each new team that comes through.
Fantastic. We do have a couple of other questions, but one that's really bugging me. I saw on the ROC curve that the Wells criteria, which is the standard of clinical practice, was essentially flipping a coin. Yeah. Did that surprise you?
Well, it didn't, because this population, just to be clear, were people that had gotten the CT. So in theory, if people were doing the workflow correctly, the people that would have been ruled out by Wells would have already been ruled out. And this is that intermediate risk population where people are like, I don't know what to do. They clearly have chest pain. Their D-dimer is, slightly above zero. Like, so we're just going to image them. And, that's where that patient population, and that's the bulk of them, frankly, now. And so that's why we wanted to use that as a benchmark to say, these people can't be helped by our current standard of care.
Great, thank you. So we have another question here from Vidur Mahajan, and the question is, how would the liability of smartphone-based diagnostics be handled? That's an interesting question. How do you regulate this and watch for drift in technology and so on and so forth?
Lots of issues there, but we can't learn what the issues are and how to make decisions about we can't do that before doing a trial and figuring it out for ourselves. Like, we can think about all kinds of failure modes, and we can try to build that into our clinical trial protocols. And we recognize that at least the approach I'm trying to take is via an established clinical trial pathway, not trying to just release it into the world and expect people to start doing it. That's definitely not an agenda I would push, and I'd kind of discourage those who have tried to do that, because again, as you pointed out rightly so, these technologies have a lot of complications in the real world. And so having a controlled trial situation where you have, again, the protocols and you have a system for doing that, to me, will help us come back and say, wow, that didn't work. Just like we kind of initially found so much automation bias that we were making the clinicians worse until we figured out how to present the information in a way that actually helped them, right? So this is the kind of learning that we all have to have collectively. But what I'm trying to argue for is that the delivery method, it's a possible way to deliver this at a larger scale, and in order to inform regulatory components, where it works, where it doesn't. That's what the purpose of the trial is.
Fantastic. And a question here from Leo Santos. What is the role of pharmaceutical companies in this journey? Have you done some work with them?
I have. I mean, I'm allowed to talk about some of it. Obviously, when I mentioned that slide near the beginning of like the assets that we all have, in terms of like the players on the field doing this work, they have an incredible amount of data. They certainly have trial data that is incredibly well annotated, at least in some cases, and has, been done in a way that informs, approval or not, right? Decisions on whether drugs get approved or not. There's a huge potential here, but the converse is also true. In other words, when you talk to some of the folks in this domain that use like CROs and others, they recognize that not only is that labeling task, the resist criteria, whatever they happen to be using, it's a fundamentally different task than the clinical work. So there's a little bit of a difference in how the person that's labeling is their headspace, right? It's a little bit different. And the reason I'm bringing that up is that small errors along the way might fall slightly statistically in favor of the drug getting approved or not, a patient doing better or not. Those little things those are human factors. And so the concern here would be, well, sure, you could go back in the archive and maybe potentially automate a system that could, get a drug to approval find a drug that maybe was on the fence and got approved. But you can also use that same system to demonstrate that maybe there wasn't a true improvement and that drug shouldn't have been approved. And maybe that's a blockbuster drug. So it's a dangerous territory right now that we're all kind of, struggling with. And then the idea of how much does the human factor matter when we talk about trying to automate some of these workflows for drug companies. But again, a startup or a new drug, I can imagine that the amount of expense that goes into a lot of the annotation, labeling tasks and decisions about change, if they're based on imaging, there's a huge potential here. And, I don't think I know of any pharmaceutical company that isn't trying to do this now.
Fantastic. And we just have time for one more question. I'm going to take one that really is two of our attendees are asking around the same thing. And this one is Jacob Rosenthal. What strategies do you have to get buy-in from physicians who don't have backgrounds in AI and data science? And Dr. B. Groen, who's saying the similar things, what do you suggest? How do you deal with professional skepticism towards this work? And some see these developments as opportunities, but some see them as threats.
Absolutely. No, I encourage skepticism. I mean, like, if you don't have a healthy culture of like, this is ridiculous, like, you have to show me that this is going to work and show me in every way that alleviates we have to do that, right? That's clear. And it's that, move fast, break things culture meets first do no harm culture. That we're in the middle of that. We're sitting in the center of this. And to be a broker between the two cultures, I think requires of the clinicians to learn just some of the fundamentals about what questions to ask about, so when you're faced with a vendor who has a really nice glossy pamphlet, can you ask the questions about what population was this trained on? How does it do in important subclasses? What modeling approach were you using? How does it generalize? Those kinds of questions I think are possible with just really not that much education. So that's one of the reasons we did that course. And I know, Kathy and others have worked on curricula for residents in particular in radiology. That's one piece of it. I think education will alleviate that skepticism, particularly if the solution is a real one. But I think in terms of threat, that's more tricky, right? I mean, you can fundamentally see, and we've had this discussion with some folks in different countries, frankly, who actually like the fact that they're the only radiologist within 100, 200 miles, right? Because that's their livelihood. And this is something that could potentially threaten that. And that's a real thing. And I don't have a great answer for you there. And certainly we are, after working in global health for a long time, just recognizing this is not going to be a prescriptive, this is not a paternalistic thing. This is a technology that is meant to be malleable and open enough that you can use it for the use case that you feel is important for you, your patients, your healthcare system, but not to be sort of prescriptive in sort of the way we're approaching this. And that tends to help as well. So, somewhere between education and just trying to provide the tools and allow them to make decisions on what to do with it, maybe those are the ways I would choose to go forward.
Excellent. And I think we're going to have to leave it there. I want to be respectful of your time and everyone's time. Matt, thank you so much. Wonderful talk. And we really appreciate having you today. Next month, we'll have Dr. Bradley Erickson from the Mayo Clinic. So please join us then. Thanks again.
Thanks, guys. Appreciate it.
Bye-bye.